In my Advanced Blockchain Tools series, I previously presented video demos of a runner and debugger for both the Ethereum virtual machine and eWASM. Based on the common JavaScript virtual machine core that can easily be extensible to support other opcodes and stack-based or functional virtual machines, I am now showing you a runner and debugger for the Near Protocol virtual machine that runs on WebAssembly. We are in Factotum, or Flexible IDE, and I have added a new plugin which takes in the interface description object at B3 and the bytecode of a Near contract, specifically their well-known counter-contract example compiled to WebAssembly, and placed at B4. We can run this tailor command and we get a form built from the given ABI, and we can call each function. Let's increment the counter with 2. A debugger window appears and we can see all the primitives called by the contract, along with the internal state of the contract, memory, and registers. We can see the input and output for each primitive, the contract storage, and emitted logs. So let's review what is happening. The input primitive takes as input the register ID, in this case 0, and writes the JSON encoded input in that register. Here it is. And this is the input. Next we have the register length, which is 11, which is needed by the WASM contract to allocate memory for the next instruction, read register. Here we are copying data from register 0 to the memory at pointer 4992. And let's take a look. Here it is. For clarity, we can only see the slots in memory that have been occupied by data. If we go back an instruction, we see that the 4992 pointer was empty and then it got filled. Now we need to read the previous counter value from storage, but there is no previous value, so the output is 0 and nothing is written in the register. Next we write the new counter value to storage at key counter and value 2, and we can see this in the code. In the increment counter function, we are setting the new value at key counter, and we emit a log. This is the hex encoded data of the log, and this is the decoded string which matches the log from the increment counter function. Now let's run the increment counter function again, and we will notice some differences. Our storage is already loaded with the previous value, which is 2. And now we see that read register writes the previous counter value in the register at ID 0. And even if it's not clear in this case, but storage write actually does the same thing and puts the old value on the register before updating it with the new value, 5. And finally, the logs. And counter is now 5. We can decrement the counter, and we get a final value of 4 and the appropriate log that we can see in the decrement counter function. We can call getCounter, and we see the returned value 4. And finally, we can reset the counter, and we see the final value turn to 0 with the appropriate log. Calling getCounter again, we get a final value of 0. This was a small subset of the contract primitives that the Near protocol supports, ran and debugged with our advanced tools.